Hello, folks. Welcome to Science Talk. I'm your host and resident oceanographer, Jim Massa. Okay, another brief little news headline published in EOS, which is a subsidiary of AGU. We have this headline here. Deep ocean cooling may have offset global warming until 1990. So what's going on? New machine learning techniques have estimated ocean temperatures below 2,000 meters, leading to a new model of warming trends. Now, when I did my ocean heat content video, I was looking at the heat content down to 2,000 meters, not below that level. So this would be new information, and it's important information. Okay. Tracking ocean temperatures have long helped scientists measure Earth's accelerating energy imbalance. Researchers at UCal Santa Barbara have now applied new machine learning techniques to extrapolate deep ocean temperatures, that is below 2,000 meters, with some interesting results. Whereas past research has shown gradual warming that has accelerated over time, new research from Aaron Bagnall, who's a doctoral student, and Tim DeVries, an associate professor, probably his dissertation advisor, has suggested that cool, deep ocean temperatures offset surface warming until about 1990. After 1990, the authors posited that more rapid warming caused a spike in surface ocean temperatures that could not be offset by prior deep ocean cooling. Now, let me pause there for a moment to give you some of my thoughts on what we just saw there. As I showed you in my ocean heat content video, we see, the heat content absorbed down to 2,000 meters. But I also showed in that video that the upper 500 meters were have warmed up much more than the next 500 and the next 500 and the next 500, those the other 1,500 meters. This is, in my view, and we're seeing this, has basically led to an increase in the stratification of the surface waters. So if you're stratifying, that means what? The thermohaline flow, as I showed in that video, is slowing down. So you are not sequestering that heat to depth, which means that you are also cutting off the communications from waters at 2,000 meters or below with the surface waters. So this stratification is going to cut off any communication with those deep waters that could keep it cool. That's my read on it. So cooling associated with past events like the Little Ice Age, which is about 14th to 19th centuries, had a lingering effect. DeVries says it takes roughly 1,000 years for surface ocean waters to circulate to the deep ocean and vice versa. Okay. Now, some of our models, especially based on the work of Wally Broker, when looking at the conveyor belt per se, so specifically that, he calculated that if you follow a drop of water from where it starts sinking in the Gin Sea, North Atlantic, and then trace it to where it returns back to the North Atlantic, is about a 575, 76-year cycle. Okay, now the conveyor belt does not go below 2,000 meters and stuff like that. So it makes sense that if we're talking about, the really deep waters below 2,000 meters, taking 1,000 years, I would say it's a reasonable estimation there. So if it does take this 1,000 years for surface ocean waters to circulate to the deep ocean and return, those cooler waters had an impact even centuries later. Because if you're pulling up some of that cooler water there, then of course you're going to cool down the surface waters. But now think back to what I just said about the stratification taking place. You're going to cut that off. Now you're not going to cool down the surface waters as you did before. After 1990, the cumulative impact of surface level warming was enough to cause whole ocean temperatures to rise. And this report appeared in Nature Communications. Bagnell's autoregressive artificial neural network, ARAN, is an adaptation of a machine learning method that he said improves on previous methods of estimating past deep ocean temperatures. Historically sparse data from the deep ocean have made it difficult, if not impossible, to accurately extrapolate whole ocean temperatures. He states, previous methods might have just taken data from 1 year or 1 month and applied some mapping algorithm to try and fill in the gaps, whereas we are considering the whole record all at once. And we're letting this machine learning algorithm or artificial intelligence algorithm make the connection between what happens near the surface, what happens deeper down. With machine learning techniques, each data point can be influenced by every other data point in a way that accounts for the ocean's dynamic properties. So in principle, the machine learning technique is learning how to adapt the relationships that it sees near the surface from around the present to prior time period as well as in deeper parts of the ocean, Bagnell said. So basically, if you're able to do this extrapolation and basically fill in temperature, then you can get an idea of the gradient, and then you can get an idea of the physics, the physical mechanisms involved that would help explain the temperature distribution that is being recreated. That's basically what the gist of all of that is. Now, of course, how good is this method? How good are the algorithms? That those are things that can be critiqued, analyzed, scrutinized, and so forth. The result is a finding that not everyone agrees with, right? That's all part of the scrutinizing the work, being skeptical, raising questions, etc. Greg Johnson, an oceanographer with NOAA's Pacific Marine Environmental Laboratory, said the lack of data about deep ocean temperatures prior to 1970 makes him skeptical about the potential accuracy of these findings. He also pointed to rising sea levels as evidence that global warming was proceeding steadily prior to 1990. In all honesty, those are extremely fair, extremely valid critiques. And I'm kind of in that camp as well. So I'm more siding with Greg Johnson on this one. The sea level has been going up fairly steadily. From the 1990s to the 2000s, 2010s, it's definitely accelerated considerably. But prior to that, it was still rising globally. And that's probably not all ice melt, which is what you'd have to conclude from this study. Bagnell responded that data on sea level rise don't necessarily contradict his finding. Thermal expansion of the oceans due to warming accounts for roughly 1/3 of the sea level rise observed today. The other 2/3 is mainly due to the addition of fresh water from land sources, melting glaciers, right? We all know that. Additionally, the historical record of tide gauges and satellites, 1993 to the present day, indicates that sea level rise has been accelerating from the 20th century into the 21st century, meaning sea levels likely weren't rising as rapidly then as they are today. So the possibility that freshwater input accounted for a larger fraction of sea level rise during the 20th century isn't out of the question. So, like anything else, when you have such a study, it's a beginning. It's not the definitive answer, the definitive, here it is, but it gives us a starting point. And from there, you can basically work to improve what it does, which will then improve our assessments, improve our modeling. But when you look at the overall point, and this to me is the overall point, is that if you increasing the stratification of the surface water, even any communications with the deep water, which might eventually make it to the surface after a millennia or so, that is going to be cut off Therefore, you're going to keep the warming. You're not going to modulate or moderate the surface temperature. It's going to get warmer and warmer. You're going to have more expansion because it's warmer. And that heat, that 226 zetajoules, of which 68% of that is in the upper 500 meters, that heat is just waiting to diffuse to the atmosphere, most of it at least, which will then, of course, have other profound impacts. So, I said, this to me is what you call a nascent study. The starting point. Give them credit for, for doing this, for attempting to create another analytical tool. Will it be scrutinized and critiqued? Of course, we saw an example of that. But you know what? That's how science works. Okay? So let's see what happens in the future. How, if they're able to improve what this technique does, and if this will hopefully help us improve our understanding of the thermodynamics of the ocean, at least below 2,000 meters, which will then help us understand better the thermodynamics from 0 to 2,000 meters, and give us a better understanding of what the heat in the ocean's role overall is with respect to the climate. So just a little something I wanted to bring to your attention, and thank you for your time, and we'll talk soon. Hello, folks. This is Jim here with Science Talk, asking you to please subscribe to my channel and to inform others of my channel and of the work that I do. Please share to social media platforms that you use. Also, as a reminder, don't forget to click the bell so that you know when I load up more videos. Finally, I ask that you support the work that I do by becoming a patron at patreon.com. Details in the description box below. Thank you for your support.